So on Friday, we talked a little bit about the different types of model matter diagrams. We talked about drawing model of matter. We talked about diatomic elements. We talked about the 5 different types of chemical reactions. We drew some MOM diagrams, and we did what's called a single replacement reaction. We worked our way all the way through that. Today, we are going to talk more specifically about something called reaction type 2, which we'll talk about what that is in a minute. So I'm going to go grab the materials I need for that. I will be right back. So here we have calcium chloride, and here we have sodium phosphate, and we had to make some observations about the two of them. So one of the most obvious observations that we can make at this point about the reactants themselves is that CaCl2. Some of you have already heard or got the hint that when I say it's a solution, you said that it was aqueous. It's an aqueous solution, which means that it's been dissolved in water, right? So this one is aqueous up here. What other things could we say about it in terms of its color or lack thereof, or something in that vein? Anything? Does it have a color? What color would it be? It is transparent. And I believe I heard somebody say that it was clear or colorless, right? Okay, so then we have, and those are pretty much the major ones. There is no odor, I'll give you that much. We don't taste, so I don't know. We also have Na3PO4. Many of you also identified that this was aqueous. There's a lot of the same things going on here. It's transparent. Colorless. And I would say odorless as well. Okay, so I can only do this one time. So eyes up here. Okay. So what I'm going to do is I'm going to take the sodium phosphate, I'm going to pour it into the calcium chloride, or vice versa. It actually doesn't matter. And here's what's going to happen when I do that. So ready, set, go. Okay. So here's the one that we did just in class here, and here is the same reaction, but it occurred this morning earlier. I don't know what's going on up there. We'll try to fix that in a second. Let me... Is that better? Yeah, that's better. All right. So now we have a product, right? And it appears that our product, okay, so that Na3PO4 was aqueous. Okay, so now we have this product, right? And what state of matter would you guess the product is? The white colored product, I'm going to tell you, is solid. So white or gray product is solid. In terms of attempting to describe the texture or something along those lines, like if I hold this up to the light, it does appear to let a little bit of light through. So we might say that it's translucent. And it had been described as slime-like earlier this morning. Okay. So we have calcium chloride, which was aqueous and transparent and colorless. Sodium phosphate, which was aqueous, transparent, and colorless. And then we had this solid product that was produced. Okay. So this type of reaction is a reaction that we call a double replacement reaction. And in this case, we know that this reactant was aqueous. We knew that this reactant was also aqueous. And I told you just now that this product was a solid. But those of you that said that the reaction still had an aqueous component to it were also correct. So in this reaction, what ends up happening is that you take two aqueous solutions, mix them together, and you get a solid product and another aqueous product. So to kind of talk about this a little bit, we are going to balance this first. And I'm just going to set up my balancing tree is what I think I'm starting to call it. And I'm going to keep PO4 together because it appears as phosphate on both sides. And so then I'm going to count my atoms. So I have 1 calcium, 2 chlorines, 3 sodiums, 1 phosphate. On the reactant side and on the product side, I have 3 calciums, 2 phosphates, 1 sodium, and 1 chlorine. So there is going to be some balancing work we're going to have to do here. And now I'm going to go and start my balancing process. I see that the number of calciums on the left side is 1. The number of calciums on the right side is 3. So I'm going to add a coefficient of 3 here, which will give me 3 calciums, but it will also give me 6 chlorines. I need to make my chlorines balance, so I'm going to put a coefficient of 6 here, which will give me 6 chlorines, but it also is going to give me 6 sodiums. So to rectify that, I'm going to put a 2 here, which will give me my 6 sodiums, but it's also going to give me my 2 phosphates, and then everybody's happy. I did that fast, I realize. But yeah. So now the next thing that we need to talk about is how do we draw the Mom diagram for this? And when we draw the Mom diagram for this, what we end up doing is Mom diagrams are really designed to show number of atoms, but also states of matter. And in this case, it's really, really, really hard to show the state of matter if you're only going to draw one of something, like in this case, Ca3PO42. That could be a solid, it could be a liquid, it could be a gas. So when, this is going to be important for reactions, when there is a coefficient of 1, okay, we double all of the coefficients so we can show the states of matter. So in this case, I'm going to double all of the coefficients by making this 3 a 6, this 2 a 4, this 1 a 2, and this 6 a 12. And then the next thing I'm going to do is I'm going to make a key for each of my atoms, right? So I'm going to say that calcium is going to be a square. I'm going to say that chlorine is going to be a circle. I'm going to say that sodium is going to be a triangle, and the phosphate, I'm going to give it a heart. Because why not? So now when I draw this structure, I'm going to go ahead and draw the doubled relationship. So in the case of it being aqueous, I'm going to have to draw 6 CaCl2s. So something like that. Thank you. And remember, when I'm drawing them so that they show the ratio of elements in the compound, right? So 1 calcium and 2 chlorines, and note that I'm also not allowing the chlorines to be bonded to each other. They're all bonded to the calcium. And because this is aqueous, I'm going to go and add some water around the whole thing to show that that particular compound has dissolved and is surrounded by water. Okay, and now I need to do the same thing with my sodium and my phosphate. In this case, I take a look at sodium phosphate and I see that it's a 3-to-1 ratio. So I'm going to make the 1 be my center part. So I'm going to do heart, 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 heart. And to that, I'm going to add some triangles. In this case, it looks like I need to add 3 triangles each. Going to draw a bond or a line to show that they're connected. And then lastly, I'm going to add water to show that they are dissolved in water, meaning that this is a true aqueous solution. And I'm just trying my best to show that they're all surrounded by water. Now, the next one, I'm going to try to show the fact that Ca3PO4 is indeed this white solid, okay? And the way that we draw a solid is it's touching and all of the components are touching and organized. So in this case here, I'm going to draw my solid to look something like this. So it's like square, heart, square, heart, square, right? And then what I'm going to do is I'm going to show them touching, but like offset. And I'm going to try to explain why in a second. So give me a second with that, please. Oops. Okay. And I'm going to connect them all here like this. Now, the reason why I showed these offset is because one of the rules that we have for drawing model of matter diagrams is we generally don't put shapes of the same shape next to each other. So if we can avoid it. So in this case here, what I've tried to draw or show is that the heart is touching a square, but it's not touching another heart. Does that make sense? So then the last thing we have to do is we have to go back and we have to draw our sodium chloride as an aqueous. So that means I'm going to need to make something like 12 triangles, circle combo platters. Something like that. And then I'm going to come back and add the circle, 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 circle. And then I'm going to bond them together with a line like so. And then I'm going to show that, that they are surrounded by water with a lot of X's. It is kind of important that we show that that there is water in between the molecules, or not molecules, compounds. That's pretty important because that indicates that it's been dissolved. And I know there's nothing more fun than drawing a whole bunch of model of matter diagrams on a Monday. Really gets you going for the week. All right, so now, so this is a double replacement reaction. And now I need to talk a little bit more about what the double replacement reaction actually is. In all double replacement reactions, right, you have the same type of starting materials. It's always starts with two aqueous solutions. Another way to potentially look at it is a compound. A compound and a compound. And specifically, the type of compound and compound is an ionic compound and an ionic compound. And if you recall, ionic compounds are made up of metals and nonmetals. So now our general formula here is going to be something like Bx plus Ay reacts to form By plus Ax. And what I want to make sure that you really get here or understand is that you have B is going to be a metal, X will be a nonmetal, A will be a metal, Y will be a nonmetal. And on the product side, B is going to be a metal, Y will still be a nonmetal. A will be a metal, and the X will still be a nonmetal. And that's important because when you do write the products for a double replacement reaction, the metals always come first and followed by the nonmetals. Now, this general formula or generic template here really allows me to identify what matches up with what on the other side. So if I have Bx reacting with compound Ay, on the other side, I'm going to get By and Ax. And the reason why this is important, this template is important, is because now we can take the elements underneath each of these and match them up on the other side. So if under the B on the reactant side is the element barium, I'm going to put the element barium here. If under the Y on the reactant side is the polyatomic ion SO4, I'm going to put SO4 here. If under the A on the reactant side is Na, I'm going to put Na here. If under the X on the reactant side is Cl, I'm going to put Cl here. So now I've matched them up and put them in the right spots. But because these are ionic compounds, the next thing that you have to do is you have to check the charges from the periodic table and crisscross them down and make sure that the ratio of metal to nonmetal is correct. So in this element, in this first compound that we just made, Ba, I know has a charge of +2. SO4 is the polyatomic ion that you all have written on the back of your periodic table is a -2. And when I crisscross those charges down, I get Ba2, SO4, 2. And so then I'm going to check my ratio of cation to anion. And I'm going to see that I can take the 2 to 2 ratio and simplify it to 1 to 1. And because we don't write ones, this particular compound is going to end up being BaSO4. And that's what we already have written here. And I know that that looks like a lot of time wasted, but it's not, because they won't all be that simple. However, when we check NaCl, which is what we're going to do next, we have Na, and according to the periodic table, it's a +1. We have Cl, and according to the periodic table, it's a -1. Some of you know where this is headed. It's going to become Na1Cl1. We're going to check our ratio, which in this case is 1 to 1. and we don't write the 1, so the proper chemical formula for this compound is NaCl. And again, I can't stress enough that it won't always be that simple. So now I'm going to go and balance this equation because that's the very, very next thing that we need to do. So I have a Ba, I have a Cl, I have an Na, and I have a sulfate SO4. On the reactant side, I have 1 Ba, 1 Cl, 2 NAs, and 1 SO4. And on the product side, I have 1 Ba, 1 Cl, 1 Na, and 1 SO4. In order to make them balance, what I'm going to do is I'm going to add I notice that my Bas, my bariums, are 1 and 1 on both sides, so I'm going to leave them alone. Going on to my Cls, my Cl is a 2 on the reactant side and a 1 on the product side, so I'm going to put a coefficient of 2 here, which will give me 2 NAs and 2 Cls. And it looks like everybody's balanced as it is. So that is how we do a double replacement reaction. There's a lot of work there. I realize that, but that's what you got to do. So, going to keep on rolling. Any questions so far?
Then would we multiply all of them by 2 since there's 1?
The question is, if you were drawing the model of matter diagram for this, would you have to multiply each of the coefficients, the 1, the 1, the 1, the 2 by 2? The answer to the question is yes. Okay. Okay. Okie dokie. All right. So I'm going to go grab the stuff for this next reaction, and we'll get started on this next reaction real quick once. All right, so this is the piece of magnesium metal that we are going to be using for this reaction. We might have noted already that it is without doing a lot of thinking about this particular one, the magnesium would be what state of matter? It would definitely be a solid. What else might we be able to say about the magnesium metal? Anybody?
Silver.
Yeah, we'll say it's like a silver color. Some people might argue that it's gray. I can tell you from like my experience holding it that it's a smooth piece of metal. It's not really rough. And then you might notice that it like does the fun little dance here. So you can say that it is bendable, I guess. All right. The next element that we need, or the next thing that we need to talk about here in terms of reactants is O2, okay? So if magnesium is a solid, what I need you to do right now is I need you to take a look around at the oxygen. Right. It literally is everywhere. So what state of matter could one say is oxygen? It is a gas. What can we say about its color or lack thereof? We're going to say it's colorless. We're going to say that oxygen really has no odor. I would say it's transparent. Now, transparent. Okay, so here's what's going to happen. We're going to go get this thing set up, and then we're going to do it. So give me a second to get this going here. All right, so I can't stress enough that you're going to not follow the directions that I give you, even though I give you directions. What I mean by that specifically is I'm going to say don't look directly at this when I do it. And now that I've said it, all you're going to do is look directly at it. There is a reason, though, why I say don't look directly at it. And the reason happens to be the fact that it's going to produce something that's going to be annoying at the very least. And the level of annoyance is really, really high. So what I'm going to do is I'm going to hold the magnesium, and this is going to happen regardless. So if I take this magnesium and I just let it sit out for like a day, a month, a week, a year, it's going to react with the oxygen in the air. I'm going to give it a push. I'm going to add some energy to the system. I'm going to create it almost like a catalyst to make this reaction go faster. You ready? What should you not do?
Look directly at it.
And yet you all are going to. It's fine.
Oh.
I told you. So like I'm looking way over here and definitely can see it.
I'm looking at you.
Okay, so that's that. That's that. Okay, so this is the product that we produced. It looks like some people have said there's a lot of ways that we could describe it. I don't know how to best show you that. Look, there it is. Okay. All right. So what I can also tell you about this is, other than the fact that the product obviously changed color. So there's an obvious color change, and you might say that it went like it turned white for sure. I can also tell you that with very little effort, like actually me just touching this, it kind of just disintegrates into smaller pieces. So we're going to say that this is probably a really brittle solid. So we're going to say that it's like really brittle. Somebody described the texture as feather-like. I like that one. Anything else you might want to say about that particular substance? Ashy, okay. And somebody else said solid, which is super important because I definitely missed that one. I usually lead with that. No, it does not have an odor, so we'll say odorless. So here we produce a white solid was produced. Wow, that is not even a word. It's like I was playing Wordle. All right, so let's talk about this a little bit. This is the reaction that actually occurs. So we had magnesium, right, which we said is a solid. We have oxygen, which we've already said was a gas. And we are producing MgO, which is magnesium oxide, which is also a solid. Okay. Now, before we go ahead and draw this diagram, we're going to go and balance this equation. So when we balance this equation, we're looking just at the relationship between Mg and O. On the left side, I have one magnesium and two oxygens, and on the right side, I have one magnesium and one oxygen. So I'm going to go and I'm going to add. I'm going to assess the magnesiums, and there's one on both sides of the reaction, so that's okay. I'm going to leave it alone. My oxygens are out of balance. There's two on the reactant side and one on the product side, so I need to put a coefficient of 2 here, which not only gives me 2 magnesiums, but it also gives me 2 oxygens. So I'm going to have to go back and add a coefficient of 2 on the reactant side for the magnesium, and then I have 1. So this is going to be another instance where we're going to double all of the coefficients. So we're going to have a 4, a 2, and a 4. The good thing about this one in terms of drawing is you don't have to draw aqueous, so that's pretty nice. I'm going to say that magnesium, I'm going to draw as a square. Oxygen, well, let's make it a circle. So if I draw my magnesiums, I'm going to put 4 magnesium squares on the bottom. Hopefully they're touching, looking pretty organized. I'm going to put 2 units of oxygen, so something that looks like this. And because it's a gas, they're going to be super far apart and not touching. And now on my product side, I'm making MgO. And so what that's going to look like is something like this. Square, circle, square, circle, and then I'm going to do circle, square, circle, square, and then I'm going to make sure that my units of MgO are connected, and there we go. That's my solid. Okay, so this type of reaction is called a synthesis reaction. We took 2 things and made it into one thing. So in a synthesis reaction, usually you start with 2 elements. That's usually what you start with. That doesn't mean that you can't start with like an element in a compound, but we usually start with two elements. And the general formula here is something like A plus Y makes AY. And then the other thing I'd like to point out with a lot of these particular, it's not always the case, but at least for the ones that we're going to talk about today, you have a metal pairing up with a nonmetal, and they're going to make a metal and a nonmetal compound. And if you might recall, a metal and a nonmetal compound is an ionic compound, which means we're going to have to check our charges and crisscross them down. So in this example here, I'm going to put an A over the Na. I'm going to put a Y over the Cl. And on the other side of the reactant, or other side of the arrow, I'm going to put AY together, like so. Now I'm going to match things up. So on the reactant side, I have a sodium and Na under the A. On the product side, I'm going to match them up. And on the chlorine, or on the reactant side, I have a Cl under the Y. So I'm going to need to make sure I have a Cl under the Y over here. I'm going to, because this is an ionic compound, check my charges. So I know that Na is a +1, and I know that Cl is a -1. When I crisscross my charges down, I get Na1, Cl1. I'm going to check my ratio, which is 1:1. And in this instance, I'm going to rewrite my compound as NaCl. And I cannot stress enough, they won't always be this easy. So now what I need to do is balance this reaction. And so I have an Na and a Cl. On the reactant side, I have one Na and two Cls. And on the product side, I have one Na and one Cl. I'm going to add a coefficient to the NaCl over here, which gives me my two sodiums and my two chlorines. So now my chlorines are balanced, but my sodiums are not. So I'm going to add a coefficient of 2 here, and then that balances everything, and that's a synthesis reaction. There are two more reaction types that we're going to talk about tomorrow. Okay. So for now, we've already talked about a single replacement reaction type, a double replacement reaction type, and a synthesis reaction type. If you have any questions, please let me know. Otherwise, have a wonderful day.